We are going to continue doing 3 more example problems involving the law of conservation of momentum. You should have these notes already. Just remember, you're going to have a quiz after this little lecture video. So make sure you have good notes, these notes, and make sure you have the template available so you can continue taking notes on that template as we do some problem solving. Again, the law of conservation of momentum was basically developed from Newton's third law of motion, which means for every force, there's an equal and opposite reaction force. When the things collide, like 2 carts collide, we did some demonstrations with those. You saw some video demonstrations with those yesterday. But it can be anything, like if my hand hits the table, my hand applies a force to the table, and the table applies an equal and opposite force to my hand. That's what this is. For every force, there's an equal and opposite. That's why there's a negative sign there, equal and opposite reaction force. Those forces act for the same period of time. My hand applies a force to the table for the same time the table applies a force to my hand. When 2 carts collide, they are in contact for the same amount of times. If we multiply both sides of the equation by time, we still have an equality. Both sides are still equal. But impulse, net force times time, is called change in momentum also. So this is negative change in momentum of A is equal to change in momentum of B. So we put the change in momentum, this is the momentum of A, the final momentum of A. We use prime to represent final conditions. So this is the final momentum of A minus the initial momentum of A. This is the final momentum of B minus the initial momentum of B. Then we just rearrange the equation to get all the before momentums on the left side and all the final momentums on the right side. We end up getting this equation, which means the total momentum before the interaction takes place must be the same as the total momentum after the interaction takes place. This is the mathematical representation of the law of conservation of momentum, written out in sentence format. This is the law of conservation of momentum, which means the total momentum before an interaction takes place is the same as the total momentum after the interaction takes place, but that's only in a closed system. And the definition of a closed system is note there can be no outside forces acting on the system itself, in this case 2 carts, and there can be no change in mass of the total system. You must know the definition or the requirements of a closed system, important to know. Yesterday we also did a couple of example problems involving collision of carts. Again, we had, you saw a lecture video on the demonstrations of carts colliding in their different situations. We're just doing this in a mathematical format of colliding carts. In this first one, we had 1 cart moving and another cart stationary before the collision. Then after the collision, cart A was stationary and cart B was moving. We're trying to find that velocity of B after the collision. Remember, the prime represents after the interaction takes place and the non-prime is before. And remember, momentum and velocity are both vector quantities, so we need to make sure we clearly identify which way is positive and negative direction in our diagrams. And so we solve all conservation momentum problems the same way. Total momentum before equals total momentum afterwards. So we look at the before situation, see what entities have momentum before, and if something is moving, it has momentum. If something is not moving, it does not have momentum. So before the interaction, only A is moving, so only A has momentum. So you only have to include that on the left side of the equation. Remember, the left side of the equation is the before information, and the right side of the equation is the after information. After the interaction takes place, A is stationary, so we don't need to include that on the right side, but B is moving. So this is the mass of B times the velocity of B after the collision. We put the values in, we get 5 meters per second for the velocity of B after the collision. We have another scenario. In this case, these masses are now different, but still A is moving and B is stationary. And then after the collision, it gives the velocity of A traveling to the west. And the west is negative, so the velocity of A after the collision is negative 1.25 meters per second. Notice I don't put masses in for after the collision because the masses stay the same. If the masses would change, then I would put that in, and we might see that as another problem coming up. But again, we solve it. Total momentum before equals total momentum afterwards. We identify what things have momentum before the collision. There's only one thing, A, so we put mass of A times the velocity of A. But now, after the collision, both things have momentum. So we need to include the momentum of A after the collision and the momentum of B after the collision. We put the values in, solve for this unknown velocity of B after the collision. Make sure we have negative 1.25 meters per second in there for velocity of A because that's the direction A is moving in the negative direction. We calculate this out. We're solving for that unknown. This is going to be 15 kilogram meters per second. This is negative 3.75 kilogram meter per second. And this is plus 5 kilograms times B prime. We have to add this to both sides of the equation to get rid of it. And so 15 plus 3.75 is 18.75 kilogram meters per second. is equal 5 kilograms times v prime. Divide both sides by 5, get 3.75 meters per second. Okay. So now we have 3 more example problems we're going to do under different conditions, things colliding and interacting in different ways. Remember, the way you solve all these conservation of momentum problems is exactly the same. Total momentum before equals total momentum afterwards. Let's take a look at example problem 3. So we have a cart A, mass 3 kilograms, traveling at 5 meters per second. So again, this is cart A. It's traveling to the east. Again, east is positive, west is negative. And the mass of A is 3 kilograms. The velocity of A before the interaction takes place is 5 meters per second. Collides with cart B. That's cart B. Cart B, mass of B is 5 kilograms. And the velocity of B before the collision is stationary, 0. Right? They collide. Now, this is a little different. After the collision, cart A and cart B stick together. We saw that in the video demonstration. We had the Velcro sides of the carts facing each other. They collide and they stick together and they move off as one entity. So if they stick together, we draw it like this. This is A and B stuck together. And so now we really just have one entity after this interaction takes place. And it's not the mass of A, it's not the mass of B, it's the mass of both of them combined. We call that M prime. M prime, very simply, is basically the sum of those two masses. 3 plus 5 is 8, so we can just put 8 kilograms there, nice simple calculation. And so this is the mass of the one entity after the collision. And we're solving for the velocity of that one entity after the collision. Right? So again, we do this the same way. Total momentum before must equal total momentum after the collision. We take a look and see what things have momentum before the interaction takes place. Since B is not moving, it does not have momentum. So we only need to include the momentum of A. So this will be the mass of A times the velocity of A before the collision. And then there's only one, if they stick together, we count that as just one entity. A is not separate from B, they are now stuck together, it's one entity. So we only have one entity that has momentum after the collision. That's M prime times V prime. We put these values in. Mass of A is 3 kilograms, velocity of A, 5 meters per second, equals 8 kilograms times V prime. Okay, 3 times 5, we divide by 8, we should get about 1.9 meters per second for B prime. So that's the velocity of that entity after it's going. It's positive, so that velocity would be going to the right. Again, everything to the right is positive, everything to the left is negative. So that means the positive 1.9 meters per second. That's how we know it's going to the right. All right, let's look at number 4. We again have cart A, mass of 3 kilograms, moving east at 5 meters per second. So we have cart A, mass of A is 3 kilograms. Its velocity of A before the collision is still 5 meters per second. Again, everything to the right is positive, everything to the left is negative, both before and after. That's true. And it's going to the right. So then we have cart B, though. Cart B has 5 kilograms initially traveling west at 2.5 meters per second. So now we have cart B that's also moving. This is cart B. The mass of B is 5.0 kilogram meters per second. And the velocity of B is going to the west, is going this direction, is negative 2.5 meters per second. Very important to have that negative sign in there. So after the collision, they stick together. We didn't have to have them sticking together, but we are this way. We can solve it either way. They stick together and form one entity. This is A. This is B. So M prime, which is the mass of this one entity, again, is 3 plus 5, is 8 kilograms. And we want to know that velocity after they stick together. And so, again, we solve this the same way. Total momentum before equals total momentum afterwards. You must have that equation shown when you solve these problems, because that is how you solve the problem. Then you look, see what entities have momentum before the interaction takes place. Since both of them were moving, they both have momentum. So we have to include the mass of A times the velocity of A plus the mass of B times the velocity of B. Momentum of A plus the momentum of B before the collision. There's only one entity that has momentum after the collision because they stick together. There's only one entity, so that's mass prime times V prime. We put the values in. 3.0 kilograms times 5 meters per second plus 5.0 kilograms times negative 2.5 meters per second equals m prime, which is 8 kilograms, times v prime. If you can solve this without doing subsequent, without doing subsequent steps, by all means do that. But I'm going to kind of do this in steps. So this is going to be 15.0 kilogram meter per second plus a negative 12.5 meters per second equals 8 kilograms times v prime. We then take 15 plus a negative 12.5, we get 2.5 kilogram meters per second is equal to 8 kilograms times v prime. Then we have to divide both sides by 8 kilograms. We take 2.5 divided by 8. We get that v prime, sorry, this is v prime, of about 0.313 meters per second. If you just want to put 0.31 there, two significant digits, that's fine also. So now what we have two carts moving before the interaction takes place. They collide and they stick together. We solve the same way. It doesn't matter how many objects we have moving before or how many objects we have moving afterwards. We always solve the same way. Total momentum before equals total momentum afterwards. And we put the values in for the things that have momentum before and after. All right, one more example problem. Now remember the video demonstration we did with the carts? When we had the plunger cart, we pushed that plunger in on one of the carts and put them side by side, and they were both stationary, which means the momentum before the interaction was actually zero because neither thing was moving. This is a similar type of situation, except we're not using carts, we're going to use a cannon and a cannonball. So we have, this is a cannon, it has a cannonball in it, all right? And it says an 800 kilogram cannon, this includes the mass of the cannonball. So this total mass, that total mass right there, is going to be 800 kilograms. And before you shoot a cannon, it's not moving, so the velocity before the explosion or the interaction is 0 meters per second. Again, everything right is positive, everything left is negative, both before and after. Then you shoot the cannon. When you shoot the cannon, what happens is the cannonball, hopefully, leaves the cannon and goes in that opposite direction, right? And says the mass of this cannonball, so this is the mass of the cannonball, I'm going to call this MC prime because it's afterwards, is 10 kilograms. And it has a velocity, I'm sorry, this is the B, this is the ball. Mass of the ball afterwards is going to be 80 meters per second. Since we have it drawn to the right, it's going to be positive. So this is the velocity of the ball, and this is the mass of the ball, 10 kilograms. The velocity of the ball, 80 meters per second after the interaction takes place. Now, we have the mass of the cannon itself after the collision. Remember, this 800 kilograms includes the mass of the cannonball. But since the cannonball is no longer in the cannon, this mass of the cannon itself is 800 kilograms minus 10. So this is 790 kilograms. And it has a recoil velocity, which means it's going to be some velocity in that direction. And that's what we're trying to solve for, the recoil velocity of the cannon. Right? So then we solve this the exact same way. Total momentum before equals total momentum afterwards. Well, we look at what things have momentum before the interaction takes place. This isn't moving, so there is no momentum. So before the interaction takes place, the total momentum is 0 kilogram meters per second. Now let's look at after the interaction takes place. Both the cannon, because it has a recoil velocity, and the cannonball are moving. So they both have momentum after the collision. So we need to include both of those. So this is the mass of the cannon after the collision times the velocity of the cannon after the collision plus the mass of the cannonball after the collision times the velocity of the cannonball after the collision. Nothing has momentum before the collision, and two things have momentum after the collision. Well, how can that be? Remember, this is the total momentum before must equal the total momentum afterwards. So let's see how this works. So then we put the values in. So it's still 0 kilogram meter per second equals the mass of the cannon, 790 kilograms, times its velocity. That's what we're trying to solve for. Plus the mass of the cannonball, 10 kilograms, times the velocity of the cannonball, 80 meters per second. I'll go ahead and do this in steps so you make sure you understand how this works. It's still going to be 0 kilogram meters per second This is still 790 kilograms times the velocity of the cannon after the collision. And 10 times 80 is 800 kilogram meters per second. We're solving for this variable, so we have to get rid of this 800 kilogram meters per second. This is plus 800, so we have to get rid of it. We have to subtract it from both sides. So this is going to be negative 800. 0 minus 800 is negative 800 kilogram meters per second. This is then 790 kilograms times the velocity of the cannon after the collision. We now have to get rid of the 790 kilograms. We have to divide both sides by that, so we can take negative 800 divided by 790. That's going to be negative 1.01 meter per second is the velocity of the cannon afterwards. Not a large velocity, but it's in the negative direction. The reason it's not a large velocity is because the mass of the cannon is so large. But if you take this velocity, negative 1.01 times 790, and 10 times 800, and add those up, this is negative, this is going to be positive. You add those up, and it's going to be 0, or real close to 0 kilogram meter per second. So the total momentum of this and this added together is going to be 0, just like the total momentum before the interaction was that took place. All right. So now, you need to take a short quiz and make sure, and you can use your notes, so make sure you have these notes available for you, and also these example problems. All right. So good luck on the quiz, and that'll be it for today.